Parametric equations?
Yeah.
Okay.
I really have no idea. Like, he didn't give us any notes or anything.
Okay. Do you have some problems to do?
Yeah.
Okay. What are the problems, and we'll take a look at them.
Okay. This one. Alright, I'm going to have to send you a picture of these ones because.
Okay. That's fine. Go ahead and do that.
Okay.
Let's talk about parametric equations while you're doing that.
Alright.
If I say this, that's one equation, two variables. But if I want to say x is equal to t plus 1, that would make y equal to t plus 1 squared. So now I have two equations and three variables. So I've taken one equation and two variables and turned it into two equations and three variables. Now you might say, well, why would you ever want to do that? And it's because a lot of things can be described better, like projectile motion. If you're talking about following the path of a ball that's thrown straight up in the air and straight back down, it's hard to talk about that path from XY coordinates. But if I plot that parametrically, where this is time and this is height, well, that ball does something like this. So when I refer to it with parametric equations, it's easier to see what the ball actually does. In other words, it goes up to this height and then it comes back down. Even though it's going straight up and straight down, I can't see much when I draw it going straight up and straight down on just an XY plane, but I can see a lot more if I turn it into a parametric equation. Now, over here, where I said, well, let's let x equal t plus 1, I made that up, but you can do that. I could have let x equal t plus 3, and then y would be t plus 3 squared, meaning that you actually have an infinite number of parametric equations that you can turn a xy function into. There's not just one parametric equation that goes with this. What they usually have you do is they give you this and they say remove the parameter. Well, if I did that, I would solve both sides for t. So up here, t is equal to x minus 1. Down here, t is equal to the square root of y minus 1. And now I set both t's equal to each other, and I get x minus y equals the square root of y minus 1. The ones cancel, and I get x squared equals y. So I've taken and removed the parameter. And I've turned two parametric equations into a single xy equation. And that's typically what they want you to do with these kind of problems. Let's have a look at what you sent me.
One through four there.
Okay. take the simple one. Hold on, I'm looking for a simple one. There aren't any simple ones there. Before we look at 1 through 4, I want to start with a simple one.
Okay.
Just so you understand what's going on. If I said y is equal to sine of t, and I said x was equal to cosine of t, what are we looking at? What is that the curve of?
Not sure.
Well, you're always allowed to add equations. So I can say, first of all, that y squared equals sine squared of t, and that x squared equals cosine squared of t. And now add that to that, and I get x squared plus y squared. Add this to this, and I get sine squared plus cosine squared, which is what? It's the trig identity. It's always equal to 1.
Oh, okay.
So I can replace it with 1. And now, what's that the equation of? A circle.
Oh.
Okay? If, let's go back and do another easier one, but still a little difficult. If I said y is equal to 2 sine of t, and x was equal to cosine of t, well, the first thing I'm going to do up here is make the sine of t equal to y over 2, right? Cosine t equals x. Square both sides. Up here you got y squared over 4 equals sine squared of t. Down here you got x squared equals cosine squared of t. Add the two equations together. You get x squared plus y squared over 4 equals 1. What's that the equation of?
Really not sure.
An ellipse. In other words, the standard format for an ellipse is x squared over a squared plus y squared over b squared equals 1. Okay. So when your parametric equations are like that, you're looking at an ellipse. When the coefficient is the same in front of both, you're looking at a circle. And then we get more complicated from there. So let's see what we can do with this problem that you have here. Now, all 4 of these shapes, I don't know what the polar equation is. Hold on a second. I'm going to have to think about these long and hard. In fact, let me look at my book. To be honest with you, I'm not exactly sure how to do this. But I think I can find it. Polar coordinates. Graphs of polar equations. I know how to do circles and ellipses. Okay. equation for a cardioid, which is this object right here.
Okay.
Appears to be r equals 2 plus 2 cosine of theta, basically. And these numbers can be anything. They don't have to be 2. Let me make sure I have the right figure. So if we can come up with the polar equation, then we can identify which graph is which. Alright. Well, we can do that, I think. Let's take this first one here and see if we can come up with the polar equation. We got x equals 4 cosine cubed of t, and y equals 2 sine cubed of t. And if we're trying to convert those two into polar equations, see, x is r. What's the polar equivalent for x?
Would that be negative x, or?
Here's the way to figure it out. There's t. X over the hypotenuse, in other words, on the unit circle, if that's 1, then the cosine of t is equal to x. And even on the non-unit circle, if I make that r, we have the cosine of theta equals x over r, so x equals r cosine of theta, and y equals sine cosine of theta. So if I go up here and in place of x, I write r cosine theta, or cosine t, equals 4 cosine cubed of t. Down here I can write r sine of t instead of y equals 2 sine cubed of t. Now I think we can make progress. Let's take this equation and simplify it. Now, I know you can't divide by a variable if it might be 0, but just for simplification here, I'm going to simplify this into r equals 4 cosine squared of t. You see how you can do that?
Yeah.
And down below, I get r equals 2 sine squared of t. So now, I can say cosine squared is equal to r over 4. Sine squared is equal to r over 2. Add the two equations together, and you get r over 4 plus r over 2 equals 1. Not very helpful. Well, that doesn't appear to be the cardioid. what is that? Well, let me see if I can find a table that has the, I think I have the table that has the, yeah, I do. D is called a lemniscat curve, lemniscat. This one right here is a lemniscat, and the equation for that is r squared equals 4 cosine of 2 theta. In other words, if we can come up with this, it's this function right here. Something that looks like this, then it's this.
Okay.
Well, we didn't get that when we broke that down. We got r over 4 plus r over 2 equals sine squared plus cosine squared, or 1. So I don't know what that one is, but we should be able to figure out the Lehman, this curve here. And it looks like wow, these are tough. Think about this a second. In fact, the lemniscat curves are r squared equals 4 sine of 2 theta or cosine of 2 theta. So in looking at our possible answers here, let's look at this one here. Let's see if we can turn that into a lemniscat, because we've got a sine of 2 theta. So all we have to do is turn the left side into r squared. Let's see what we get when we play with this one here. We got x equal 3 cosine of t, and x is r cosine of t. So if that's equal to 3 cosine of t, then r equals 3. That's the equation of a straight line. But we also have y equals sine of 2t, and y is r sine of t equals sine of 2t. Well, sine of 2t is 2 sine t cosine t. So now I have r sine t equals 2 sine t cosine t. If we take that step right there, aha! Square both sides and I get r squared equals 4 cosine squared of t. That's the equation of a lemniscat. So that one goes with D. 2 is D.
Okay.
And that's pretty much the way you have to do all of these. In other words, that leap we made for circles and ellipses is kind of similar, not quite, because we didn't go to polar when we did that. All of these curves are polar curves. So we need polar equations to define these curves. And we just came up with one. There was the polar equation that number 2 changes into. So we're going to take each of these parametric equations and try to turn it into a polar equation. We're going to then look at the polar equation and see, well, which of those curves is that? In other words, I know the basic format for the Lima-Scat curve. That was this format, and that's what these two equations turned into. So let's just keep doing that. Let's look at number 3 and see if that turns into something familiar. We got x equals 2 cosine of t plus 2 cosine squared of t. And since x is r cosine of t, in other words, I'm going to convert this to polar, first of all. Well, I can divide everything by cosine of t, and I'm left with r equals 2 plus 2 cosine of t. And that is the equation of a Limacon curve, which is this top left one. Do you have a book that has your typical equations for some of these curves?
I have a book on any of the.
It's hard to find. I actually have to look in my book, and there's a certain kind of equation for rose curves. There's another kind for Lima shots. There's another kind for cardioids, which is what this is a cardioid. But the format for a cardioid is that right there. R equals 2 plus, or some number plus some number times cosine of t. That is the general format for a cardioid, or it's called a Limacon curve. It's pronounced actually Limacon. No, Limason. It's a Limason curve. Okay, so let's take our fourth equation and see if we can turn that into something that looks familiar. Because we've got 2 goes with D, 3 goes with A. If we can figure out 4, then we'll be in like Flint. X equals sine t minus t cosine t. Well, instead of x, we're going to write r cosine t. So if that equals this, and then we have y equals cosine t plus t sine t. And instead of y, we're going to use r sine of t. Okay, so we got these two equations now. If we square it and add these two equations, should work. Let's square this top equation. It gives us r squared cosine squared of t equals, this isn't that easy to square, but it's a binomial, so we'll square it like we square any binomial, minus 2 sine t minus 2t sine t cosine t plus t squared cosine squared of t. You with me?
Yeah.
I'm going to do the same thing to the bottom. I'm going to square both sides. R squared sine squared of t equals cosine squared of t plus 2t cosine t sine t plus sine squared of t. Okay? Now I'm going to add these two equations. I'm going to add this to this. You can always add equations. What do I get? On the left side, I can factor out the r squared, and I get cosine squared plus sine squared. That's what I get on the left. That becomes 1. On the right, you'll notice that I got a minus 2 of those things, and I got a plus 2 of those things. These things are going to cancel. This thing down here is 1. This thing up here is plus sine squared of t plus t squared cosine squared of t. Alright, and now all we got to do is figure out this becomes 1. So now I've got r squared equals 1 plus sine squared of t plus t squared cosine squared of t. So all we have to do is figure out which shape that is. Let me look in my book and see if I can find it. I'm looking at analyzing the spiral of Archimedes. This is an Archimedes spiral. And the general equation of that is r equals theta. Can I narrow this down to r equals theta? I don't think so. I don't think there's any way I can pull this sine squared and that cosine squared out. So I don't think it's the Archimedes circle. The only other one is this one up here. And what the heck is that? You know, my book does not give the formulas for these things. This book doesn't. So I have another book that does. Unfortunately, it doesn't give that particular one. Hold on. I'm looking at your problems right here. We got the same book, don't we? Yeah. I'm looking at this book right now. Same thing. So I'm in the right chapter. We should be able to figure out these 4 questions. How is the question? In other words, this is at the end of the chapter before you turn it into polar. Oh, I think I see how they want you to do these. And it's probably not the way I've been doing them. Yeah, these exercises come at the end of the chapter before you get to these polar curves. So the way I was doing them, we don't even know what these equations for these polar graphs are yet. Which means they want you to answer this by coming up with a table.
Okay.
Wow. Notice that on this same page, if you look down, there's tables here.
Oh, yeah.
And this is the very basic way to analyze parametric equations. In other words, just do a direct substitution. If these are my 2 parametric equations, and t is minus 2, then x is 0 when t is minus 2, and y is 1 minus 3/2, or minus 1/2. So you see the way to do 5? and 6?
Um,
You know how to complete those tables?
Really. Oh. Yeah, I'm not sure how to do that.
Well, let's start there, because it's that technique that they want us to use to solve 1 through 4. I'm pretty sure. I was ahead of myself. But let's do 5, and then I think you'll understand this a little bit better.
Okay.
Okay, so if we make a table, see, once we make a table of the XY values, now we can graph it. So when t is minus 2, what's x? Plug in minus 2 for t into this parametric equation.
Would be 0.
When t is minus 2, what's y?
Negative 5.
Whoops, hold on. Excuse me, I wrote it wrong. It's divided by t.
Oh, okay.
Okay? Okay, so when t is minus 2, y is minus 1/2. When t is minus 1, what is x?
That'd be, oh, okay.
What's y?
That'd be negative 2.
Next column is when t is 0. What is x?
Negative 2. Oh, 2.
What's y?
Wait, how is x 2?
Because all we're doing is plugging in 0 for t. X is equal to t plus 2, so when you plug in 0 for t, x is equal to 2.
Okay.
When you plug in 0 for t in this one, what do you get?
1.
Let's call it infinity for the moment,
Okay.
instead of undefined. Because it actually is defined. It's infinite. This number becomes infinitely large when t goes to 0. Okay, let's finish the table, because this is how we're going to solve 1 through 4 also. When t is 1, x is 3. When t is 1, y is 4. When t is 2, x is 4. And when t is 2, y is 2.5. Okay? Now we can plot what this parametric equations look like, because we have a set of xy points. When x is 0, y is minus 1/2, right there. With me?
Yeah.
When x is 1, y is minus 2, right there. When x is 2, y is infinity, that means there's an asymptote there. Y is infinite. When x is 3, y is 4. When x is 4, y is 2.5. There's our curves right there. Looks to be hyperbolic functions. In other words, once I've taken my two parametric equations and made a table And I now can basically eliminate the parameter because I have a series of xy points, coordinates, and I can graph it and then connect the dots. Okay? So let's go back and do one again and see if we can figure out which of these curves it is. X is 4 cosine cubed of t. Y is 2 sine cubed of t. Let's make our table. Here's t. What kind of increments am I going to use?
Be using like pi over 2.
Yes, exactly. So let's start with minus pi over 2. When t is minus pi over 2, what is x? It's the cosine of pi over 2.
Yeah, I remember.
0. Here's your cosine. Here's your cosine curve. And goes the same on the other side, so the cosine of minus pi over 2 is also 0.
Okay.
What's the sine of minus pi over 2? Sine curve looks like this. Or that's pi over 2. So the sine of minus pi over 2 is minus 1. Cube it, you still get minus 1. Multiply it by 2, you get minus 2.
Okay.
So you can see what we're going to do here. Next comes 0. Well, the cosine of 0 is 1. So that's x is 4. Sine of 0 is 0. So y is 0. Then we're going to go pi over 2. And x is 0. Y is plus 2. And we're going to go pi. Well, cosine of pi is negative 1. So x would be minus 4. The sine of pi is 0. Let's plot that just from that much.
Okay.
That's 4 points. We might be able to figure out what kind of curve that is. In other words, we're going to plot it on the xy grid. When x is 0, y is two different things. It's minus 2, but it's also plus 2. So immediately we know we don't have a function.
Okay.
Okay? Notice that's not a function, this isn't a function, this isn't a function, and this isn't a function. So we're okay not having a function. When x is 4, y is 0, and when x is minus 4, y is 0, which curve are we looking at?
That'd be B?
Yeah, it's got to be. It's the only one that fits those 4 points.
Okay.
So that's how we're going to do all 4 of these, is
Okay.
make a table. I couldn't figure out how they wanted you to do these because my book doesn't even talk about how to do these. But because it's the chapter before you get to these curves, they want you to do it the simple way, which is to make a table and then plot your XY points from that table. So that's the way you're going to do 1 through 4, is to make tables.
All right.
All right. Are there any more on this page that you need to do? We could go through each one of them, but I think you get the hang of it now, don't you?
Yeah. The next.
I've got the page in front of me, so if you just want to give me the problem number, I've got it.
Yeah, it's 6 through 15 by 3.
Let's look at 9.
Okay.
6 is just like 1 through 5.
Okay.
You're going to make a table, plot the XY points. 9's a little different. Tell me if your 9 is different than this, but usually these problems don't change from addition to addition. We might have a different addition. When you have something like this, there's an easier way to do it than making a table. And that's to solve each one for t and then set the other side equal to each other. So solve the top one for t. What is t equal to in the top?
Wait, on mine there's also infinity. Okay.
Right, there's t only goes from 3 to 5. And that's helpful. In other words, if we were making a table, we would only let t be 3, 4, and 5. We wouldn't have to go 0, 1, 2, all of those numbers. But this exercise says eliminate the parameter and identify the graph of the parametric curve. So the way you eliminate a parameter when you just have polynomials like this is to solve each side for t, if you can do it. What's t equal to in this one? Right?
How did you get that? Sorry?
Just algebraically solve that for t. Okay? You with me? Same thing for y. Well, y is going to be, we got 4t equals 9 minus y, so y is going to, or t is going to be this. So I now have this, and I have this. The t's are the same, so I can eliminate the parameter by setting this equal to that. So I got x plus 3 over 2 equals 9 minus y over 4. And so all we have to do is figure out what that's the equation of, because it says, and identify the graph of the parametric curve. What kind of graph is that? Multiply both sides by 4. Let's solve it for y. I'm going to move y to the left. I'm going to move everything else to the right. What's that the equation of?
It looks like
it's a straight line.
Yeah.
It's a linear equation. It's a straight line with slope minus 2 and an intercept of 3. But here's the kicker. It's not this straight line. In other words, there's our intercept. There's the slope of minus 2. When I draw that line, it goes up to infinity and down to infinity. Whereas our line is constrained by the fact that t only goes from 3 through 5. Well, when t is 3, you have an x of 3 when t is 3. When t is 5, you have an x of 7. So our line only goes from 3 to 7. In other words, if this is 3 over here and this is 7, we're only looking at the part of the line from there down to here.
Okay.
Here, I can, in other words, the line we're looking at is not the full line, it's just this part of it, from here to here. And we would erase that part, because t only can be 3, 4, or 5. And that correlates to an x going from 3 to 7. And a y going from, well, when t is 3, y is minus 3. When t is 5, y is minus 11. And you can see from our curve that this part of the line goes from minus 3 to minus 11 on the y-axis. So parametric equations, probably the biggest single thing that's different from rectangular is that t is frequently restricted. And the moment you restrict t, you restrict the total dimensions of its xy line. In other words, that line ends right there and ends right there. It doesn't go to infinity in both places. And it's because t only goes from 3 to 5. So that's the extra thing with parametric equations that is different. In other words, just eliminating the parameter and graphing it is not enough. When we eliminated the parameter, we were looking at the equation of a line, but that didn't account for the restrictions on t, so we have to add that into it. Because all it does is it makes the line have a beginning and an end, and it's just not extended in both directions. All right. Let's see. We got time for another one here.
Okay.
Let's do 12. You have to do 12, correct?
Yeah.
Okay, well the first equation's already solved for t. Let's solve the second equation for t. T would be plus or minus the square root of y plus 3. So now setting this t equal to this t means that x equals plus or minus the square root of y plus 3. What's that the equation of?
I don't really recognize that.
Square both sides.
Like a parabola, or?
The parabola shifted down by 3 units. Only I can't really say that it's this because I haven't restricted t, but it's going to look like this. It's only going to be part of that.
Okay.
In other words, they're telling us, oh, no, I guess on 12 they don't restrict t. So for 12, we've eliminated the parameter, and the curve is the entire parabola going all the way.
Okay.
Okay? In other words, 9 and 10 in the book have t restricted, which restricts your final curve. But if you don't restrict t, in other words, if t can be all real numbers, then you end up with just a parabola. So those two parametric equations in 12 equate to this parabola. $15, you have to do 15?
Yeah.
X equal 4 minus t squared, y equal t. That's good. That's already solved. Let's solve for t up here. T equals plus or minus the square root of 4 minus x, I believe. In other words, I move the t squared to the other side, move the x to the right, take the square root of both sides. Got it?
Yeah.
Now set this t equal to this t. So I got plus or minus the square root of 4 minus x equals y. Now, if I'm trying, the problem says solve for x in terms of y. So my next step would be to square both sides. Notice that when I square the left side, it takes care of that, plus or minus also.
Oh, okay.
Is that the equation of?
Just a straight line again, right?
No, it's a sideways parabola.
Oh.
In other words, if I move the x over to here, I got 4 minus y squared equals x. And this is a parabola that opens this way. You've had conic sections?
What section?
Conic sections? In other words, you've had these sideways parabolas, right?
Yeah.
Okay. The way I always remember it is the thing you started, the very first thing they taught you in terms of quadratics was this one. And that's this standard. When you have x equal y squared, instead of y equal x squared, that's a horizontal parabola. So x equal y squared would be this parabola. Well, the parabola we're looking at is x equal minus y squared plus 4. So instead of opening to the right, it's going to open to the left because of the minus sign. And the plus 4 means it's moved does it move it up or does it move it left and right? That I'm not positive. I think it moves it left and right so that it would look like this, basically, where this is minus 4. I might have that wrong. In order to figure out which curve it is, just plug in some points. Here, we can do that real quick. We're looking at x equals 4 minus y squared. So when y is 2, x is 0. So when x is 0, y is plus or minus 2. There's your sideways parabola. When y is 0, x is 4. So here's the parabola we're looking at. In other words, this 4 is a shift to the right of 4 units.
Okay.
It's not a vertical shift anymore. Means vertical shifts would have to come from something being inside there, like y minus 2 quantity squared. That would be a vertical shift of this horizontal parabola. All right. Let's see. I'd like to do one that has cosines and sines in it, just because it's a little tricky. 19 through 22 are not such creatures, but let's do one of them anyway. Let's see, we did 15. 18's the same as the others. Those are just polynomials. So let's do 21. End it on that. And then I got to go because I have an 8:30 also. But to do 21 requires a little bit of a leap of faith. Not leap of faith, but a little different technique because of the trig functions. In other words, I can't solve for t here very easily. I could say that t is the inverse sine of x over 2, but that's not the way to do these, because I don't have any way of turning that inverse sine into anything. However, what I can do is this step, and this is worth memorizing because it's going to work for ellipses and circles. If x equals 2 sine t, then sine t is equal to x over 2. And if y equals 2 cosine t, then cosine t equals y over 2. Now square both sides of both equations. And I get x squared over 4 equals sine squared of t. And I get y squared over 4 equals cosine squared of t. And that's the step that's not obvious at all until you've done a few of these. Now we've got it in the form where I can add the two equations, and when I add the right sides I get 1. So what am I looking at here? I'm looking at x squared over 4 plus y squared over 4 equals 1. Multiply both sides by 4. What's that the equation of?
Circle.
Yeah, except it's not going to be a complete circle, because notice that in 21 they restrict t from going from 0 to 3 pi over 2. Well, I'm pretty sure if memory serves me right, that to draw the entire circle you got to go from 0 to 2 pi. If you go from 0 to 2 pi, you get a whole circle like that. Which means that if you go from 0 to 3 pi over 2, you're only going to get that much of the circle.
Okay.
And you'd have to verify that by plugging in other words, let t go from 0 to 3 pi over 2 and see if you get the full circle or you just get points in the first, second, and third quadrant. And I'm pretty sure you're going to get points just in the first, second, and third quadrant. You won't get the entire circle. And in fact, parametric equations actually have a direction on them. You put this into your calculator and watch it draw. If you put it in as a parametric equation, your calculator will start here and it will go like this. And it'll stop there. If you let t go from 0 to 2 pi, then it'll finish the circle. If you let t go from 0 to pi, it'll just do the top. All right. I got to run, Daniel.
All right.
Hopefully that's been helpful.
Yeah, well, thank you.
After I realized what chapter we were supposed to be on, not the next one, but the previous one. All right. Have a good week. Talk to you next week.
All right.
Bye-bye.
Bye.